roll. Take it away.
Okay, go to the agenda there. So we started out in the kind of restarted our effort to work on the tracking software after about a year and a half delay. And so the last half of it's going to discuss kind of the tracking things. But in the first half of this presentation, we're going to go through kind of the existing as and L drive systems, and then its interface to the system one. And then we'll get into the tracking related kind of thing. So uh, I'm going to try to go relatively quickly through the early parts, but certainly stop me and ask any questions and or make any corrections. Parts of these items I'm not as familiar with as others. So first slide is a drawing of the azimuth subsystem, and I'm not sure who's the author of this slide. It came from somewhere in past history. I think some of the people that originally set up the system put it together, but I find it a real useful overview. Yeah. So in the lower right corner is kind of the center of or at least the focus of the system one interface to it, which is the Copley motor driver. And basically it controls the motor and sets the rate of the motor. And it accomplishes this by it has an AC output to the motor, which is the power source for the motor. It controls the current going over there to control the motor torque, which in turn controls the rate of the motor. And then it has a feedback from an internal resolver in the motor that allows it to sense what rate the motor is moving at, and it adjusts it so that it moves at the desired rate. And then that motor drives through a multi-stage gear train. It goes into some, a chain drive into a mixing gear, and then into this main gearbox, and which then drives a pinion, which drives a ring gear. And I don't really have any information on what the gearing is through this whole thing. Just know that it's geared dramatically down, and maybe in the multiple thousands to one gearing ratio. So, and one thing to note on here, there's a brake system. The motor itself seems to have an internal brake, and also there's a brake on the mixing gear. The Copley driver will control that brakes when the Copley driver's in motor controller is enabled. Then it energizes those solenoids and relays and such, which releases the brakes, and then it proceeds to control the rate. Just as one thing I want to point out is the power system that goes to the Copley. It takes a 240 volts input. I believe that comes from downstairs, from basically the circuit breaker in the base of the tower turns that on, and that goes into the Copley, and it also goes to a 24 volt power supply, which is the power source for the digital logic and controller in the Copley. So one of the things as far as I know, there's no switch other than the power breaker that can turn it on and off. So I, I think it would be good to have just as an aside, it's good to have a switch in the tower and in the ops building that can turn that off.
Now, Lewis, there is a second breaker that controls the 240 volts into the system that's in the tower at the third level next to all this equipment. And
Okay.
so if you're in the tower and you need to shut it off, there is a breaker there in the tower that does shut off the power to the system.
Yeah, that's good. I mean, that's from a human safety point, that's a good thing to have up there. You don't want it coming on when you're fiddling around with the kit equipment. I think it
Especially,
would also be good to have it as it is in the elevation with the VFD power switch. It'd be useful to have it in the ops building rather than having to go out to the tower to turn it off. But
yeah,
that's not a major thing. Anyway,
Yeah, if we could get a contactor similar to what we've got for the power in the hub, that would work out really well with, big stop button in the control room. Couple things I'd like to add here. That ring gear, for people that haven't been up in the pedestal, that ring gear is, what would you guess, like 8 or 9 feet across?
I'd say 10.
10 feet across. And you actually, when you go up on top, if you need to climb up to the elevation axle, you go through a hatch and you actually climb through inside of that ring gear.
uh,
Um, Also, the brake that's there is a dead man brake, which means the brake is applied when there's no power. So power is applied to remove the brake. So it's similar to brakes on a train or on a semi. If the in those cases, if the pressure goes away, the brakes go on. Here, if the electricity goes away, the brakes go on. Okay, go on.
yeah, and I want to make a few comments about the Copley and its controlling the rates. The rate is input. It can be input to the Copley via servo pass, either through a serial gate or a CAN network, or in this case, it's through a analog differential analog signal that's down. It's that plus minus 10 um, on the two arrows there. It's a differential. I will say that right now the system one controller is not passing a true differential signal to it. And so it still works fine, but what you lose is the differential gives you noise immunity, but if you don't use it in that manner, then you don't get the benefit of the noise immunity. So, but so system one will assert this enable signal over on the kind of right center down at the bottom, but um, and it apparently goes through, and Bill, you probably know this routing better than I do, through the limit switches and then into the Copley to enable it. So if the limit switches have been, limits have been exceeded, they would not allow the enable signal to get all the way to the Copley. But
Yeah, that's true. And you'd have to override the limit. And we've done that a couple of times where we accidentally drove it into the limit switches.
yeah, and so this analog control voltage is a plus minus 10 volts, and anything from 0 to plus 10 is a positive rate. I believe that's clockwise, and then anything negative will be a counterclockwise. And the magnitude of that voltage tells them the speed. So the Copley sees this, and um, one of the capabilities of the Copley is it will ramp up uh, the rate up to the commanded value. It doesn't just immediately slam it. And actually, that ramping factor is a tuning factor in it. And the same thing is if you command it to a slower rate, it'll ramp it down to that rate. And so that, helps with in terms of jerking the mount around. And the other note is that when you deassert the enable, the controller will ramp the motor down to 0 and fire, and at that point fire the brakes. And actually, I think the firing of the brakes is a timer from started at the time it starts ramping down the motor rate. So that provides for a good deal more smoother startup and shutdown. I had always been concerned, like from the manual control panel, that we were, it was stopping it abruptly, but it doesn't, by the description, seem to do that. And then the final thing I haven't covered on this diagram is the as encoder. And that encoder runs off a separate kind of drive chain as or a separate gearing chain than the actual drive mechanism. So the good thing about that is that the actual measurement of the axis position doesn't have that, is not affected by any backlash that's in the drive part of it. There may be some very minor backlash in that mechanism, but I doubt very seriously it's very large. But so right now we have a 16-bit our encoders are a primary encoder, and that comes back across Ethernet to system 1. So that's kind of I think that covers this. If there's not any questions, we can go on to the elevation. And elevation in some ways is similar at a high level. There's a motor controller, it controls the rate of the motor. And I will emphasize that both motor controllers are controlling the rate of the motor, not of the actual axis. And but since they're direct coupled mechanically, the axis rate is directly proportional to it. So in the case of the Allen Bradley, there are some differences. It's a VFD controller, variable frequency drive, and it doesn't control the current so much as it outputs a specific, or outputs a frequency to control the motor. And it also, in combination with that specific frequency, it selects a voltage that's appropriate for that frequency. So, and that basically sets the rate of the motor. Another difference is in the elevation, there's no feedback mechanism from the motor back into the motor controller to tell it, that it can sense the rate. I think it basically just depends on the frequency, basically setting the rate. It's kind of a blind, no feedback approach. And then the gear train is a bit different too. It goes into this mixing gear, which drives this horizontal shaft. And that shaft drives 2 ball screw drives. And what those do is convert that rotary motion into linear motion. And the other end of the ball screw drive is attached basically on a lever arm for the elevation axis. In this drawing, the the two shafts that have the gap between them, that's the actual elevation axis. And then you can see that the ball screws are attached to, offset from that, thus providing lever arm. So in this case, the rotary motion of the motor is in essence converted to linear motion on the ball screw, which then through the levering action converts back into rotary motion on the elevation axis. So in just one note, in the azimuth axis, the motor rotation rate is directly and linearly, or the azimuth rate is proportional to the motor rate directly. With this linear actuator in it, there's a variation for a given motor rate across the elevation range, and we measured this one time a while back, and if both ends of the elevation range 0 and 90, the rate is higher than the rate in the middle for a given. It's not a huge variation, but it is probably 10 to 20% variation. So it turns out the tracking mechanisms that we've been using are relatively insensitive. You don't have to have a really precise rate to deal with it. The elevation axis also has a brake on it, and it is controlled by the VFD. And of course, if you lose power, it'll also trip. And in the VFD is similar to the azimuth Copley in that it ramps changes in rotation rate up and down, and it also ramps down the motor rate before firing the brake. So in that sense, it's very similar to the azimuth. Then down at the very bottom, well, let me see. I'll talk about the control first and then the power. But the control there are actually two switches you can signals you can control: the run forward and run reverse. As you would expect, run forward runs I believe that's the up direction, and then reverse is the down direction. So the system one has to set one or the other of those depending on the direction it wants to go. And then there's a speed input that's labeled down there. And in this case, the voltage range from 0 to 10 volts but the direction is controlled by those two run forward and reverse signals. So it's an analog signal. The speed is analog, but it's not differential as it is in azimuth. On the power side, the whole VFD is powered by 240 volts coming from, well, I guess it's from the circuit breaker that Bill was talking about, through a contactor that doubles the voltage to 480 going into the thing. And the contactor is controlled by VFD enable signal that switch controlled. So basically it switches 24 volts through the coil, and that will, when it's energized, it will apply power to the VFD. And similarly to the there's an encoder, position encoder that's independent of the drive chain. and it's the same encoder, same model as on the AS 16 bits, and there's also a 12-bit encoder. And on the 16-bit, it's routed through Ethernet to the system one. So that's a quick run through of the two access systems. Now we're going to kind of go through a set of charts to, see how the system one gets access to those signals and uses them to control the.
Louis, what
Yeah.
what does VFD stand for?
VFD is variable frequency drive. And so, that just alludes to that's the type of motor controller it is. It varies the frequency of the electrical power sent to the motor to control the rate.
So disabling the VFD disables the elevation, but it appears that it does nothing to disabling the azimuth. Is that correct?
That's what the drawings in those two show, but I don't know if there's something not captured.
Yeah, I can clarify on that. The VFD opens the main power contactor, and so that turns off both the 480 and I believe it also turns off the 220 to the azimuth, to the Copley.
So a better name for that would be on and off.
Well, yeah, it was, I guess, it comes down to technical nomenclature and how the originators labeled it. But we've always used VFD, and even VFD is somewhat of a misnomer because, it's, I question whether it's really variable frequency or variable pulse width, right? So, yeah.
Well,
But it
I would
does,
just say the Allen Bradley refers to itself as a variable frequency
yes, it
drive,
does.
but
Yeah.
I don't know the technicalities of it.
That's right. You're right.
And
I
the Allen
agree
Bradley,
with Roger in that I think it's always I've wondered, is it VFD turning it off? Does turning that power off also disengage the Copley or not? I was never really sure of that. Uh, so
and unlike the Copley, so the Copley can be driven, either through the variable voltage or the CAN bus, but the Allen Bradley is only voltage driven by voltage, correct? There's no, is there a serial interface on there at all for controlling it?
I think there's a serial interface, but I haven't spent a lot of time studying that. I can go back and look that answer up in the Allen Bradley motor manual, but it's the Allen. One nice thing about the Allen Bradley is it has a LCD display on it, and it can't display a lot of information, but you can specify what you want it to display. And I think it defaults to displaying the frequency that's being input to the motor, which is kind of an indicator of the right. If you know the number of poles in the motor, you can figure out the RPMs from that frequency. But
Okay.
the drawing doesn't specify the make and model of the motor, so I've not been able to look up much about it. So,
All right, thanks.
let me see. So this next slide, the interface signal is just kind of a summation of those various signals that we talked about in the diagram and I'll just review it quickly. The AS drive controller, to make it move, you have to hit it with an AS enable. And then you use the voltage to control the direction and rate of the AS drive. Let me see, for the elevation, it's similar, but there's not a single enable. You either specify the direction up or down and should never specify both at the same time. And then use the voltage to specify just the rate, not the direction. And so the magnitude of that voltage will specify the rate. So the next chart is really just to understand kind of, I'll just call it the cabling between the motor controllers and the various ways of controlling it. So the motor controllers connect into this terminal block 9, which is in the upper area of the tower. And you can recognize it because it's kind of the wires are going every which way but loose. So in this terminal block 9, I call it that because that's what I've seen on some information that came from the originators of this thing. I think it might even, terminology may come from like a one of the towers in Boulder or something. But at any rate, a cable runs from terminal block 9 in the upper tower down to a terminal block in the lower part of the tower. And that's labeled tower TB2. And that cable carries all these signals. There may be other things on it, I'm not really sure, but it definitely has these signals. And then from that terminal block in the base of the tower, it goes to a terminal block on the rack where the manual control panel is. Originally, this cable went over to the trailer, and there was actually a cable plus 1 or 2 signals were on another cable, and I don't know if they were consolidated or how. You may know the answer to that, Bill. But so from that terminal block, the well-known Jones plug is connected to it. And that Jones plug can be either connected to the manual control panel, in which case you control the mount from that panel, or it can be connected to the motor controller interface on system 1. And in that case, the operator console controls it. I will note out off of terminal block 9, there's a cable with a Canon, I guess, jack on it that potentially, in fact, there was a control paddle up there that you can, manual paddle that you could connect to it and control it from out there. I've heard that it might not be operational at this point, and potentially, the motor controller interface could be connected there if it was moved to the tower.
Yeah,
Yeah,
when Ray and I were up there, we found that the transformer that was driving it had actually burst, and was so we basically disconnected that, so that no longer exists.
Okay.
yeah, there was a little power supply up there that gave it the plus and minus 15 volts that it needed, and that had failed catastrophically, and so the manual control block that you could run out of the tower is no longer functional, and that used a round connector as well. It was a mini pin round connector, but we could always interface the joystick into a Jones plug interface and have that as an option down on the ground.
Right. So let me see it. Now we'll want to look into the motor controller interface internals to, just to understand, the hardware that interfaces between the operator console and the Jones plug. And basically the elevator up and down and the as enable are switch closures, and they're driven by these relays, and the relays are controlled by the operator console via a serial over USB interface to the Namato relay board. And then the analog voltages are generated by the slab jack tic tac, and the ops console interfaces to that lab jack tic tac through the lab jack, and I think that's also a serial over USB interface. From my memory may not be quite right. So there's some other features in there. There's a watchdog timer on the lab jack, which the software has to reset. Otherwise, the lab jack will assert the signal, which engages or disengages the relay. And then what that does is it's basically the same thing as turning the VFD off. It's just a switch in series with the VFD switch. So that's kind of a mechanism that in case the software hangs or something, the mount won't just keep running forever. It'll get turned off. And then the other thing is the LEDs are controlled through relays. That's kind of a overkill approach, but the relays were available and it was a straightforward way to do it. So the software is actually what sets the clockwise and counterclockwise down and up values for those LEDs. All of these lines are connected to the Jones plug, and the numbers on there are the pin numbers for the Jones plug. So it's pretty straightforward. I will note that we had a problem during the Artemis mission, and the problem was with the tic tac. It on the as-axis DAC stopped functioning or functioned improperly. And so that was the issue we had when we got a new DAC in there. It worked again. So, and that's one of that kind of precipitated, thinking about this whole interface and tracking and all those things, which has partially resulted in this presentation. So,
Louis, I'm trying to show, in case anyone's unfamiliar with it, this is a Jones plug.
Oh yeah. Fortunately it's a very robust plug because we unplug and unplug it. I think it would be good to have some sort of switch in place of moving the plug, but I'm not sure quite how hard that would be, but it would make for a better transition. So, and I have looked at times for switches that had enough poles to control it, but I wouldn't say it's real common.
Yeah, I've got a couple of 25 pin RS-232 switches that could be used for that if we wanted to put that in the back of the rack.
Yeah, I think
But we'd have to change everything to a 25 pin DSEB.
right. It's not a whole lot of signals, but it'd be some work. And
Yeah.
I mean, primarily the primary requirement is it would prevent. You want to make sure that you can't get both connected at the same time, which
Right.
The Jones plug ensures that you can't have it plugged in twice. So.
Yeah, the other thing we discovered, you can't move the Jones plug with the power applied.
Right. Yes, that's if you do that, then even it can cause trouble.
Yes.
So yeah, that's something we need to emphasize from here. So that's kind of the overview of the whole interface and how it works. I haven't talked about the software. We'll get into a little more about that, when we get to the tracking methods. But when we first started down this path, one of the problems that we faced was we didn't know how to map that drive signal voltage to an actual axis rate. And so the way we attacked that problem is we said, well, let's just apply signal voltage and measure the axis rate that it actually achieves. So that basically encompasses, all the way, the mapping all the way from the input of the voltage through the motor controller, through the gearing ratio and everything. It takes all of that into account. And then we can use that mapping to command the axis to known rates. And the way we initially did that is we used the manual control panel because we didn't have any other method at that time anyway to set a voltage and then use a voltmeter to measure the voltage it was set to. And we had software that would run and record a time tag and the encoder position data. And I think it was running at 100 hertz, but is that correct, Lynn?
Yeah, I think I remember it being 100 hertz. It was definitely
So,
faster than 10 hertz.
so one of the things I was concerned about is time tagging accuracy because we're going to use the time tags and positions to compute the rates. And by running it at 100 hertz, at worst, on the average, the time tag would be off by at most, half of a hundredth of a second, plus or minus. So we got that data, and the way we determined the rates was, what we ended up doing is, well, first I'll say we recorded the data for 10 seconds, which unfortunately we probably should have recorded it for a little bit longer. These were with the 12-bit encoders, and for the slower rates, it doesn't change the position measurement very quickly. But so we looked at, in the data, we looked for when the encoder changed and then noted that time, and then looked for when the encoder changed the next time. And we know how much one bit is. It's like 0.089 or so on the 12-bit one, and divide that by the time, and we got the rate. I put the data into Excel and plotted it, and also did a linear curve fit. And I'm going to show some. Actually, let's jump forward to the next slide, and then we'll jump back to talk about the issues. These are the plots that came out of those measurements. And let me see, I think it's rate on the horizontal axis and voltage on the vertical axis. And those little colored shaded blocks are the curve fits. And so in this case, we express volts as a function of the rate. What we really need in the software is going the other way, so we can, rearrange the equation to do that. But and basically we found, the signal, it was fairly linear, and any non-linearities were probably more due to our measurement technique. And that was true on both as and L. What we found out on elevation, well, let's go back to the previous slide. I can talk to it. The elevation rate issue, we found that when we decreased the voltage down to around 0.2 volts, then the axis was moving to like 500ths per second. But then when we reduced the voltage below that, it stayed at 500ths per second, even when we set it to 0. So basically, there's no way to get the elevation axis to move at a 0 rate, short of turning it off. And the 0.05 degrees per second is about an order of magnitude larger than the fastest elevation rate that we would encounter, like when tracking stellar objects. Within the solar system, the rates would be different, but they would be pretty close to those stellar rates. So we weren't sure if we quite gathered that data correctly, and we went back and reconfirmed that in some later measurements at the site. In effect, so I believe this limitation is due to there's a minimum frequency that you can command the motor to on the elevation axis, which translates to a minimum rate. And I don't think there's any way to work around that limitation. Yeah. So that, it's not a problem in our current tracking technique, but if we wanted to do a smoothly controlled kind of PID-based thing, then it becomes an issue. So you see on the azimuth rate, when we analyze the data, the lowest rate we saw was 0.01 at around 0.2 volts. And we basically saw 0 rates at that below that. But due to the 10-second duration of the measurements in 12-bit encoder, we wouldn't catch, encoder bit changes in that short of a duration for that resolution. So we really didn't know what happened below that. Later, when we were doing some testing, I was out in the tower and Glenn commanded it to some really low voltages, and I noticed that the shaft for the azimuth was turning at lower voltages than that. So it made me realize, we probably just didn't, it was turning too slow to measure it on the 12-bit thing. So that was one of the driving factors of going back out and remeasuring that. So we can skip on to the next slide. So that's what we did recently in June. We went back out. We were re-looking at the possibility of doing, PID control on the axis in particular. Wanted to see if it would, had low enough rates to where it would, work fairly smoothly. So we set out to measure rates. We did the test slightly differently. Instead of using the manual control panel to set the voltage, Glenn has this test tool that can command the lab jack to specific voltages, and that's a little easier to use than the front panel. So we use that to set the voltage. We recorded time tags and 16-bit encoder data. And we also ran it for 30 seconds as opposed to 10. So that gave us a longer period of time to measure these slower rates. And then we basically derived the rates in the same way we did earlier. We took the time tag data and measured, how quickly it changed in the position data. Then plotted it in. This plot is zoomed in a little more than. This plot is the data we collected. It zoomed in a little more, and what it basically shows is, we can go. you can see the curves have roughly the same slope, but their y-intercepts are different. And so if we go on to the next slide, we see the words for that. We found that we can set the as rate to 0 or to a voltage anywhere below roughly 0.01, and the as will run at basically 0 rate. Just to explain this minimum non-zero rate, basically down to 0.01, it would run at 0.001, and then below that, it went to 0. And I'll talk about why I think that is a little lower. We found that the fit harm, slope, and offsets, basically the slopes were consistent, the offsets were different. And we also, the linear fit harms were relatively consistent with our earlier measurements also. So that was good. We didn't measure the full voltage range that we had earlier because we were focused on the slower portion of the curve. So what we found is there's a dead band between plus or minus 0.1 volt range where all of those voltages are interpreted as 0. And I believe, I looked at the Copley manual, and there's a parameter in there called the deadband parameter. And basically what it says is the Copley will interpret any voltage, the absolute value of the voltage less than that as 0. And the intent of that is to keep the Copley from responding to very low voltage noise on it. And now I haven't gotten on and confirmed that that parameter is in fact set to 0.1. And in general, we need to kind of look at the controller and go through all the parameters and record them so that if we ever have to replace it or repair it, then we can reestablish it back in its current configuration. The other thing I noticed is the deadband is slightly off center from 0 volts by 10 to 20 millivolts or so. And I think that results from the calibration of the LabJack DAC. Each of the LabJack DAC comes with some calibrated values from the factory, and each DAC is a little different. When we installed the new DAC in the system, we have not updated the calibration constants for the new DAC. So we're running the new DAC with the old calibration constants. In general, it doesn't make a lot of difference, but it can, make a difference in millivolt range. So,
Yep. Louis, let me just interrupt for people who may not, Louis is talking about a new DAC. During the Artemis 2 effort that we went through, the dish actually started driving in the wrong direction. And there's been a lot of research into that. There are differing opinions about exactly what's going on, but the replacement of the DAC did fix that problem, or at least made it go away. So they had the DAC had gone bad for whatever reason, and they replaced it with by DAC. That's a digital to analog converter. So it's basically a volume knob that you can run digitally. And so that's what they're using to change the voltage that's going up to both the Allen Bradley and the Copley. So when they replaced that, they did introduce, it sounds like looking at these charts that DAC may not be calibrated the same way the old DAC was. That might, account for some of that offset. I just wanted to say why the DAC got replaced.
Right.
So,
yeah, I kind of mentioned that earlier, but
sorry about that.
but it's good to reiterate it. I think there was, you know, questions and concerns and confusion about what, what went wrong. So,
Yeah. The only other comment I have for this, Lewis, is that we do have those calibration constants, and all we have to do is switch over to them.
right. And yeah, I don't think it's an operational problem. It's not going to make very little difference. As I mentioned earlier, our tracking algorithms don't depend on having a real precise, um, accurate rate. If they're in the right ballpark, then the algorithm's going to work okay. So, as I mentioned, we went down there to look at this. Can this support, more of a continuous commanding of as versus the step approach that we have been using? And it appears like, based on this, being able to command down to 1,000th degree per second, you should be able to use that to track continuously on, extrasolar objects, moon, planetary objects, satellites within the solar system, basically all the types of objects that we try to look at with the system. I think Roger had a concern. I think the as brake sounds like it makes a fairly large amount of noise. He was concerned that it may not be up to the task of staying continuously in a released state. And so we really don't know the answer to that question. We
Yeah,
need
and I have
to,
no idea if that's a legitimate concern or not. I just wanted to raise it. There's also the concern that there's a minimum speed that it's recommended that you run the motors, because the motors actually their turning is part of their cooling system. So the motors are spec'd with a minimum RPM to safely operate without building up too much heat.
right. Yeah, that's another one. I should have captured that on this list of bullets. So even though it indicates that we could probably support PID operations, I did some more work on PIDs, and we'll see in a couple of slides. And I think at these lower rates, I think there's potentially a backlash issue because the PID could command amount to plus and minus rates fairly frequently, and that would cause it to go through this backlash cycle. And so that concerns me a little bit. We really don't know how much backlash we have, but given that the as-axis has the chain in its gear train, it almost certainly has some level of backlash, but we just really don't know what that number is.
Well, considering that the ring gear and the pinion gear driving that ring gear have teeth that are on the order of about an inch, I think, most of the backlash may be in that system right there.
Oh, you think so?
Yeah.
I so
But
that's kind of,
did I understand you right to say that you think you can get down to continuous drive?
I think um the motor controller can support those rates. Of course, there's this issue that Roger raised about, is the motor moving fast enough to, cool itself? And I don't know the answer to that either. But I think there are issues when I went and looked, I had done some PID analysis earlier, and I kind of updated it and relearned it. And what I saw is that it would kind of go between with the rates. Well, let me backtrack a little bit. The rates for azimuth, most of the rates are below 100th of a degree per second. And our encoder resolutions around just about half of that. So at some point, when you get below 0.01, so probably somewhere around 0.005, we're not getting real timely updates from the encoder because it's waiting for the resolution to get exceeding the bit flips.
Yeah.
So I think it's going to be a little erratic controlling rates that are below 0.005 and in a fairly amount of the sky at sidereal rates results in azimuth rates that are in that range.
Yeah,
So,
that's right. You're going to be well at high zenith positions in elevation. Your
when
rate's going to be much
actually, I
lower.
think, I think the PID will work better at higher rates than these really low rates. But
Yeah.
you're right, when you get into elevations above, but you have to be pretty high, like 88 degrees or 89 is when you start getting into the rates that start to get pretty high.
Well, anything crossing the meridian is going to have an elevation rate change of 0.
Yeah,
Right,
elevation. That's not what I meant. The azimuth, when you go to high elevations, the azimuth is for
right,
sidereal is very low.
Oh, okay. But
right,
also bear in mind that the elevation's very low, like 0, when objects cross the meridian.
right.
Yeah.
And that's really when you think about elevation, when you have the minimum rate we can command at is 100th degree per second, but you really need close to 0. That gets there's essentially no way to do it without just stopping them out.
And that's what we do now is it's what we call a
Right.
bang, bang, bang control system.
What I had hoped for, is you could command it to 0 rates and not hit the brakes.
Yeah.
But you can't do that in the elevation. We think you can do it on the azimuth. It's something that we kind of need to confirm, but because the azimuth can go down to really slow rates, or even 0, we can command it to 0 and it'll go to 0 without firing the brakes. So that's kind of the difference between as and L.
All we need to do is get a wrecked Prius, steal the ECVT stuff off of it, and put 2 motors on each axis. Simple, right?
Right.
We've actually talked about that. Yeah,
Hey,
so
that would be cool. We could have a hybrid drive.
that's right. A CVT transmission would allow us to slew fast and track slow.
Yeah.
Right. If y'all can work that up, that'd be great.
It goes right in there where there's now a little chain.
Yeah, it's
Right.
right there on that chain drive, right?
Yep. In between the chain, it replaces the chain essentially.
Right.
I hope it replaces something because that's a pretty long set of gearing to go through. Now to want to get back to tracking, we've kind of talked about, a previous briefing about our current tracking approach and the modified approach. And I'm just going to kind of go through it moderately quickly here to kind of refresh everybody's memory. On this, I'm going to talk to it through this diagram. Basically, and this diagram is for one axis. It could be as or L, but it's just an example to show how the algorithm works. The horizontal x-axis is time, and the vertical axis is the axis position. And so in this case, you see, the axis starting out at a lower number. The numbers are so small I can't read them, and then it just continues to increase. So that slope of that line is basically the rate that the object is moving in that axis direction. And then what you see on the bottom left, I haven't really emphasized it, but you see the slew into getting the axis near the object. And what happens is basically these dotted lines are upper and lower thresholds that we try to maintain the object between those boundaries. And so on the slew, we start out at a higher slew rate for azimuth. It's like 0.4 degrees a second, and for elevation, I believe it's 0.2 degrees per second. But when we get within 1 degree in slewing, we switch the mount rate to the stepping rate, which you can see on this shaded box is 0.1 degree per second for as and 0.05 for L. And so once it crosses that threshold, then it turns the mount off and lets basically the object will keeps moving along its slope. And eventually the error between where the mount is pointing and where the object is exceeds that threshold. And at that point, we turn the mount on and step it. And and what we do is we turn it on and step it until it's inside the threshold. So that's what you'll see in this curve. It steps, drifts, steps, drifts. And so it keeps it, the max error is the threshold. But what you end up seeing is it ends up having a bias off of that. And that results because it doesn't step the axis all the way to the other boundary. It basically steps the axis for 1 second and then turns it off. And the reason it's 1 second is because the update cycle is once per second. It turns it on, and then the next update cycle, it sees, oh, I'm within the threshold, and turns it off. And it pretty much works that way on all rates. The difference is for slower rates, the step will go higher up and get closer to the opposite threshold. And sometimes for lower rates can get all the way to the object, but it just results in a bias. And one of the things that initially were thinking is by controlling the threshold, you could control how often it updates. Well, it turns out the way the algorithm's implemented in the current version, it's pretty much insensitive to the track threshold. It just, and so really what happens in this current mode is if you decrease the track threshold, it reduces the bias from the actual object path, and it doesn't really change the update rate. And we're trying to minimize the update rate because when we turn off from the step, it fires the brakes and stops the mount. And there's a certain amount of wear and tear on the brakes and the mount from that. So the two basic problems we have with it is it has a bias, and we can't set the update frequency based on the threshold. So we can go on to the modified step tracking. This is plotted in the same manner. And the primary difference is that when we step the mount, we step it all the way over to the opposite threshold and then let it drift. So what happens is that's a longer drift, and and thus it's we have to do the steps less frequently. And that's the basic idea behind it. And it removes the pointing bias, but it doesn't change the max error. The max error is still the threshold. And by modifying this algorithm this way, you can change how frequently it steps based on the track threshold. If you tighten the threshold down where you bring the distance between the two thresholds down real tightly, then it's going to switch more often, step more often, and then if you widen it, it's going to step less frequently. And basically, you can set the threshold, according to the mission you're running. If you're running at like 400 megahertz, the HPBW is really wide there, and you can go much longer without, degrading your signal strength. Now, if you get up in the S band or even this 8 gigahertz, then you may need to tighten the threshold down to, maintain your signal strength. So that's the trade. Actually, we've prototyped this algorithm and run it for one day down at the site, and it pretty much runs as advertised. We need to make another trip and make sure it's working correctly, and we understand everything about it. And so that's a prototype that's kind of a standalone. It needs to be integrated with the overall System 1 software, so there's some more additional work to do that. So that's the second approach. And then the third approach is the PID tracking approach, which is a continuous updates to keep the mount on the trajectory of the object. And I've implemented a simulation of a PID loop in Excel, and then a model of how I think the mount controllers would respond to that. And so the simulation is somewhat subject to the accuracy of that modeling, but I think it's close enough to draw some conclusions. And this is one case. The target rate is 0.004 of a degree per second in azimuth. That's a pretty nominal azimuth rate that you would likely encounter. And to show the PID settings, let me talk about PID servo control first. Basically, we control the axis position through a proportional integral derivative algorithm. And we have this addition of rate feed for, which, since we have knowledge of the object rates, we can feed that into the PID and make it a little more stable. And the way the PID works, on each update cycle, it gets the current position of the mount, it gets the current position of the object, computes the error of that, and then it uses that error information to compute a commanded rate. And the commanded rate is based on these P and I and D parameters. And so proportional really tells you, we'll set the command based on how large of a error we currently have. Integral tells you'll adjust the commanded rate for how much the accumulated error on the mount is. In other words, for each update cycle, you keep adding in the update error. And And so if you're behind the object or in front of it even, that accumulated error starts adding up and it causes the a larger adjustment to the commanded rate. And then the D is the derivative, and it really looks at how much did the error change from the last time versus this current time, and this really acts as a dampener on the tracking so that it kind of keeps the controller from making wide changes. One note is the PID can come up with a commanded rate that's higher than the max rate, and so what the algorithm does is basically limited it. The way you find the commanded rate, you add up the P and the I and D command along with the current object position, and that forms your overall commanded rate. Let me see. And so basically the P and I and D are gain factors that tune how sensitive it is to those errors. And so, in general, the larger the gain, the, more responsive it is to that error. And so when you go out and fill this thing, there's a certain amount of tuning that has to be done to adjust those parameters to make it work smoothly. And one of the things, what you'll see on this example, getting back to the example, is that it is maybe hard to see that the grayish plot is the commanded rate. What you can see, it's like a sawtooth bouncing from plus to minus. There are small changes, but nevertheless, it is reversing the direction of the mound, which will then, result in the, going through the backlash. And I've tried detuning the PID parameters to make it, and you can reduce that, but I haven't found that I can change it. I have done some research, and there are potential ways you can modify the algorithm to deal with backlash, but to do that is going to take extra work, and it might end up in not really avoiding backlash issues anyway. So it gives a nice fine control, but it may cause some instability due to backlash. So going to the next plan, we were basically we've looked at, okay, should we just finish the modified tracking approach, or should we go forward and do more work on the PID approach? Based on this issue with backlash, we've currently decided that we should just complete the modified tracking approach, get it fielded. It'll give us an improvement in ability to tune the update rates. And so that's what our current plan is. One note about step tracking, it really avoids the backlash issue. The steps are always in the same direction, except actually there are two cases. Roger pointed out the other case. When your azimuth gets close to 180, the elevation switches from going one direction to the others. But that's like a one-time only switch when you cross the meridian. And so that's not a major issue. And then the step tracking might reverse direction when it slews to the object, if it comes in from in front of the object, then it has to reverse direction to go in the direction the object is going in. But again, that's a one-time switch, and thereafter it just steps through, turns it on and off, but doesn't switch direction. I wouldn't say the PID approach is dead, but it would need further work, and just seems to our best response is to get the modified algorithm fielded and running. So to do that, these are some steps. We've already prototyped the tracking algorithm mods, as we've talked about. We tested them with the simulator in the Springs and also once at the site. We need to do a little additional site testing to get higher confidence. And then we need to integrate that algorithm into the operational code, and Glenn can talk about that a little more than I, in detail. Test that in Colorado Springs and then test it and field it at the site. I think we're kind of thinking in terms of timing that we wouldn't introduce this before the Venus work this fall. We'd wait till a little less hectic time to do that. I think Glenn also has some mod, and maybe you want to talk to it, for the some mods related to Horizon, so we can support the Horizon vehicle pointing a little more smoothly.
Yeah, so I'll just go over real quickly. When we were doing the Artemis work in February and March and April, we put in code to allow basically a single object to be tracked via the data coming off the JPL Horizon website. What we're trying to do right now is we're trying to make that more generic in the sense that the operator can select an object off a list that we provide, and then it will go using that object ID to go get the propagated position data and track it that way. That way, if we want to track different deep space objects, the Horizon database does a really good job of providing pointing data, and we can access that data across the internet and point them out. So we're working on that in parallel to this. So Phil Gage is finishing up the work that is mostly a GUI operator interface type thing. Once we get that completed, we're probably going to field that sometime either the summer or fall. And then this other thing that we're talking about, this modified step tracking, would be sometime in midwinter probably.
I have short question.
Sure.
Is it any wind related issues with tracking?
Pardon?
Do we have any wind related issues when we do tracking, especially on slow speeds? Sorry.
It's not. If there's any ringing, it's below the resolution of the encoders. I think one of the, I didn't really.
I'm asking about wind. So the antennas is pretty have a pretty big surface, and it's wind resistant. So basically, if wind blowing in certain direction and you have to track in opposite of wind, so the motor needs to be controlled with higher current or something. So do we have any like PID? PID basically supposed to control that, but is it in current algorithm? Is it any wind related compensation exist or not?
In the system one, there's no compensation for that. In the motor controllers themselves can handle that. They, like, for instance, the Copley controller has it controls the current going to the motor, and it's doing a control loop at, like, I think it's 14 kilohertz. So it's running many times a second. And then it's controlling the rate of the motor at, I think it's 8 kilohertz. It attains position feedback from the resolver in the motor. So if the wind adds extra, it results in needing extra torque to hold it or something. The motor controller should handle that pretty well. And basically the system one is a position controller, and it uses rate to control the position, and then the motor controller controls the rate. And so that's kind of the way the current system works. But the motor controller has, as far no special mechanisms in it for those types of things.
And the sensor, it's a gray code encoders, absolute encoders, correct?
Yes.
Which are you talking about the position sensor?
Yes, position sensors.
It's a resolver, and it's not an optical. It's a resolver type.
And
Okay.
what is resolution there in
Um,
degrees?
65,
Oh.
536.
So it's about
16 bit.
0.005 degrees.
It's 5,000.
Oh, okay. Okay.
So it's, the 12-bit encoders are slightly under 0.1 degree, and the 16-bit ones are at a 5,000th of a degree. And one of the things I have noticed is I never see any jitter in like the last bit on the encoders, so they seem to be fairly solid. But
Well, there's one other piece of that, and we generally, by policy, if we're over about 35 miles an hour, we shut down.
right,
So, we don't want to stress the mount and over torque anything. So, we can kind of tell when the wind is above that, and we've actually measured it, and held off on operations when it's above 35.
Okay, thank you.
We should make that automatic, really.
And another thing, it was a issue. I mean, not the issue, but it was mentioned the temperature when you run motor on slow speed, and it needs ventilation. So it makes sense also set up the temperature sensor on the motor just in case, for fire safety and for motor safety.
yeah, I'd have to go back and check the thermal controls on the controllers. I'm not sure if they'll shut it down when it gets too hot or not. I need to look at that. We've certainly not. I've never witnessed that happening, but
Yeah, I think our duty cycle typically is I don't know, I'm guessing here is probably around 20%. We run the motor and then it sits there for a while, and then we run the motor. So it's not getting hit a lot.
I think it's actually around 8 to 10% based on some earlier analysis I was doing to see how frequently we were turning on and off the mount. So it is low. And
Okay, and go ahead.
And it's even lower when the object rates are slow. So
Mhm. Yeah, and this Friday I'm going to be doing some experiments with the encoders. And one thing I might do is just, especially if there's a bit of wind there, is to just watch the encoders and see if I see any jitter.
right. I mean, I don't. You potentially could enable the azimuth and command it to 0 rates and leave it enabled, and you could see, if the wind is affecting it.
Well, I was thinking of just having basically everything turned off. Actually, that brings up another really sorry about this very specific question to either you or Glenn. Can the encoders accept multiple connections? In other words, can you have multiple clients talking to the encoder? By my understanding, it uses Modbus.
Yeah, most definitely you can do that.
Awesome. Okay.
Yeah, well, this actually, Alex typically connects and when the system's running too. So definitely.
Okay. Yeah, my goal for Friday is to just go down there and see if these encoders are behaving the way I think they're behaving before I invest many lines of code.
So that's really all we had.
I just have
And
one
I
more
think,
comment is that we're preparing to go down to the site sometime in the next week or so to collect that data that we're talking about in the perform additional step tracking algorithm. I think I've got some modifications that we want to test out down there and collect more data and see how we're doing.
I I have a couple of issues for you guys. The the test that we ran this past Saturday, with the new uh, Pulsar data collection software that I've written, highlighted two things related to your system. First of all, we had uh, this this new software is sufficiently efficient that we can do multiple pulsars in one session. Well, we tried that. We did 2 pulsars. And guess what happened? Going from pulsar 1 to pulsar 2, right in the middle, your system, when it was slewing from one pulsar to the other, in the middle was the sun. And so we ran right into the sun.
You should have
So
got pop-ups that said you're
we
approaching.
got pop-ups, but I'm not interested in pop-ups. I want
Okay.
to go from A to B. And if the sun's in the way, I would like you to think of a way of avoiding the sun if I command it to go through the sun.
Yeah, there's software called sun avoidance that we do not have implemented,
Yeah.
but it could be
Well,
implemented.
that's one thing. The second thing is with the new software, I think I can set up a day or even weekend pulsar tracking uh, scenario in the software. But what I would like is an application program interface to your software so that I could command your software automatically and not have to stop everything and go over and reprogram your software and then come back to my software when yours is ready. I'd rather just send you guys what it is I want to do next.
Okay, so what you're looking for is some type of automatic or automated commanding of the telescope based on scripting.
Yes, probably via local area network Ethernet interface, UDP, TCP or something would be the best interface for that. You already have your computer on the LAN, so that shouldn't be too hard.
So are you saying you want something external to the site commanding the mount?
No, 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 no.
Okay, just
I
checking.
want it on the LAN. We can restrict it to a local area network other computer that we can find a way to restrict this so it doesn't come from remotely.
Okay. So
Uh,
basically
there-
what you're asking for is a way of scripting commands uh, from either, some flat file or something like that that executes and runs the system.
well, it could be just commands and you let me worry about the file, or I could send you a file with timestamps, but that's overkill. All I really want is uh, to send you a command, here's what I want to do next, would you do it for me?
Okay, well, I'll have to think about that. I mean, it sounds easy up front, but there's beginning conditions, ending conditions, and error conditions, so we have to think
Of
about
course, I didn't say it was trivial.
it. Yeah.
I'm just saying, I am now your customer and I would like to ask you for new features.
Could you please write a requirements document for that?
I could, I absolutely could.
There you go. Can I make a comment question on the sun avoidance?
Yeah.
My understanding is that we have sun avoidance and the mount will stop if it's
No, it will
directed.
not.
What
No, it will
happened to
not.
that? It
does
used to.
not.
No, no, that never existed. I asked at the very beginning, do we want to stop the mount to the club? And this was years ago. Do we want to stop it? And everybody said at that time, no, we do not want to stop it. We said we'd put up pop-ups to say, hey, you're approaching the sun. And then it's up to the operator to decide what they wanted to do. That was
Oh, well, I misunderstood that we had asked actually that it wouldn't go into the sun.
no, I definitely asked that question. So, but
Ah,
once again, it falls back to a requirements document, like we just said.
yeah.
Bill,
No, we ran
also,
into that.
it sounds really simple on the surface, but let's say you're approaching the sun, um, from the west, and you're coming straight toward it, and you stop. Well, now you're stopped, and guess what happens?
Well, the sun tracks into you.
It
But
tracks into it. So yeah, I mean, there's
I think that's
sun
why,
avoidance is not a simple problem to solve.
but I'm
actually,
sorry, I just understood that we had it, and now it was a
Um,
misunderstanding.
No, well, I had never seen the pop-up before, but I sure as hell saw it Saturday. And it was a complete accident. I just picked two pulsars and Ray and I looked at it and said, oh my God, to get from this pulsar to that one, we have to go through the sun. And sure enough, the pop-up came up and it kept going and we didn't know what to do. So we just let it go. I don't know how close to the sun it was, but close enough that I saw the pop-up for the first time ever.
so Rick,
Yeah.
All you have to do is just cancel the command. There's a cancel command button right there, so you can just cancel it.
Yeah.
Yeah, it's just that we had never seen it before, so it threw us, for the first time. Next time I'll know what to do when I see
Yep.
it.
Well,
But
if you didn't already melt the mount or the antenna, we have melted at least one antenna in this
Yeah, I
process.
saw the pictures of that one. Yeah, no, I didn't stop on the sun. We were, I don't know how close it came either. I don't know how big this box is that says you're too close, but we were too close, but I don't know how close, too
I believe
close.
it's 10, I believe it's 10 degrees.
Oh, 10 degrees? Well,
Yeah.
we may have just skirted the edge of it. I don't know. But we didn't have any problems. I'm just saying if the destination is outside the box, then it wouldn't be rocket science to have your software say, those guys are going to go through this sun area. I'll just go around it with an algorithm that goes around it to get from here to there.
I totally agree.
Rick, going back to your request about being able to, for your software to be able to drive the dish, are you envisioning something like you give a right ascension and declination to the software and then it goes off and
could
does the
be,
right thing?
yes, it could be that simple, yes.
Okay.
I'd like to have you consider another option. Basically, in the current System 1 software, it can command the System 1 receiver. And particularly it's used in scans and such like that. So right now, the design of the System 1 software is kind of set up to be it's in control and then it can command, RF type things. So, I'd just say you might consider how if it would be easier for the System 1 to have a list of destinations to visit, and then when it gets to one, gives you a message saying, okay, start your RF thing and pulsar thing.
I, uh, I would like to suggest two things. First of all, I sent out my trip report late today, but I didn't send it to you guys. And I think I'll send your team a copy of my trip report because it describes among other things, why I'm doing what I'm doing. So you have a better idea when I ask you for something, why I'm asking. And secondly, I've tried for quite a while to get together with you guys physically. We're not that far apart to discuss these kind of things offline. I would still like to have a meeting with the System 1 team at some time in the near future because I'm starting to touch on things that I need to know more about your philosophy, and I think you need to know more about mine, and we don't need to do that in this meeting environment.
Sounds good.
Sounds good. That's fine. So that's kind of where we're heading in the near term is try to get this modified step tracking working appropriately and getting it installed. I agree. If we're going to address sun slews or something, we probably should address it at the same time. Don't you think, Lewis?
Yeah, the sun slewing, like Roger says, is harder than it looks.
Yeah, it's definitely harder than it looks.
You know, I think we're going to need the higher resolution tracking or the modified tracking for anything we do with Venus because the control um, window is going to be much tighter than it has been in the past,
Right.
especially if we're at 13 centimeters. And
Right.
so anything that keeps it more accurately on the object, I think the better will be.
Even
Okay.
more so with the 8 gigahertz deep space
Well, yes.
experiments.
Yeah. As we go up in frequency, the window becomes narrower and narrower. So it's got to be a much more, the modified tracking would be far superior to what we have now.
Yeah,
You can
one,
also tighten up those the excursion lines, can't you?
Yep.
If you really wanted to keep things very, very close on.
So I think what I was saying there, Roger, was don't wait for the sun avoidance issue to implement the modified tracking is what I was alluding to.
Okay, I guess what I'm saying is I think that you can already get that to some extent by just tightening up the roll back to your one of your step diagrams, if you would, Glenn. Yeah, that's good. So the yellow and blue lines can't those can be specified, correct?
That is correct.
Yeah. So if you
actually,
right out, go ahead.
I was just going to say it's actually one parameter. It's
Yeah.
the width from the either line to the object. I mean, so we use the same parameter. It's just a question of plus or minus.
But what I'm saying is it is to be more accurate, all you have to do is tighten up those lines. So
Right.
it may not be optimal, but you can get that accuracy right now.
Right.
Not
But
right now.
Oh, not right now?
No,
No,
this is the new step track approach that we're
Well,
working on.
well, go one more to your old one. I mean,
Yeah.
if you tight because again that yellow and blue lines, those dotted lines, that's a specified value, correct?
That's correct. But I think as Lewis was saying earlier this evening, by changing those threshold values, it doesn't really make it any better. Is that correct, Lewis?
well, I guess it doesn't help the update rate, but what it does is reduce that bias. It
Yeah.
brings the bias closer to the object path, which reduces your tracking error. And it doesn't really change the update rate, so it's kind of you don't lose much. There aren't many bad effects from doing that.
So see if this is a correct statement, is that we can get better accuracy with what we have right now, though that isn't the long-term goal.
Correct.
Okay.
Well, the other thing I would just say in terms of limits of what you can do,
Bill's shaking his head.
there's one aspect of this problem that we haven't really addressed here, and that's what is the bias in the encoders? That's what we run calibrations for. And to really nail that number, you need to run the calibration with the feed that you're going to use. We've never run that calibration with the S band or the 8 gigahertz. We've only run it on the 1296 and the 1420 feet. Now it appears, just based on our results, they must be fairly close because we've had success with the S band and the 8 gigahertz. But in truth, we need to run the mount cals on and nail that bias. I think with the newest calibration approach, we can measure that bias down to probably like 200ths of a degree or so, 200, 300ths.
But what I was shaking my head about is here you always have a bias. In this control methodology, there's always a bias error, no
Well,
matter
what I'm
what you do to calibrate it. If you go to the modified version, then you split the bias and you're always crossing the line.
Yeah, what happens in this one is the average error is biased. In the modified one, the average error should be real close to the
Zero.
Yep.
object.
Oh, I agree.
And what I'm really stressing is that in the way I view tracking accuracy, there are two aspects of it. How well do we know, how accurately the encoders read the actual position? And that's independent of how you track. And then there's the tracking aspect of how well does the tracking, how close does it keep the mount on the object? And you have to combine those two errors, and you have to combine those errors for both axes to get an actual off-bore site tracking error.
That's true. Yeah. But here, if if you move left or right of the center line,
Right.
you right. Where the other one, it doesn't matter. You're always off one side of the center line.
Right.
Yep.
Well, like I say, it depends on the object rates. If the object's moving really slow, that step will come closer to the object, but it's still biased.
Yeah.
But
Well, and
Yeah.
at 8.4 gig, Roger and I, right, Roger? I mean, we were surprised how close this thing is, right?
Yes, you've all done a very good job because it was dead on
Yeah.
to
And
the beacon.
well, one of the other things is I know you've done the work on the feed and the mounting part. Apparently, whatever you've done is very consistent with the way it was. The last calibration done on this was it was when we did the official fielding of the 16-bit encoders. We did a calibration at that time. I believe that was in the spring of 24, I think. I have to go back and check my notes. So we've been running with that same calibration, and that was done on a 1296, I'm pretty sure.
Yep.
And we changed the feed out, changed the mounting mechanism and all, and it still seems to be fairly close. But we don't know that for sure.
I think that's
All right.
where we're
Are
heading.
there any more questions? I'm sorry, Glenn, what?
No, I think that's fine. I was just saying this is where we're heading as best we can.
yeah, I think that'd be great. You guys have done a fabulous job getting all of this nailed
Oh,
down and working and calibrated. So I think it's very good when you get to the modified approach. I think it'll be awesome.
I have one quick one, Glenn, or what's the Modbus rate that you're using?
Let's see, the Modbus itself is internal to the encoders.
Yeah,
We're basically querying the encoders across TCP/IP.
right.
So let's see, I think I'm doing it 100 times a second, I think.
Ah,
So
okay,
we're reporting it 10 times a second and,
right,
and using it about once a second. So that's kind of what we're doing. But with the new approach, it won't be like that anymore.
Yeah,
right,
I will add that with the modified step tracking approach, we're planning, or at least I believe the prototype is running at 10 hertz instead of 1 hertz.
right.
So what that'll allow is, right now at 1 hertz, the object's going to go slightly outside of the error threshold. And by running it more frequently, we'll limit that amount by.
Are you are you are you doing programming in what, Python,
Java.
We're doing all our work in Java.
Java?
Yeah,
Okay,
it's fast. It's real time.
Yeah. Not as fast as C or C++, but it's certainly fast enough for what we've
right,
been
right.
doing.
Yeah, it's a good thing it's slow. The universe is slow enough for us to get things done. We're not trying to track a drone.
And we're also not
And,
trying to do 1,000 hertz updates. Those are kind of tough with the type
Oh
of
man.
devices we're using. So,
Okay, thank you, guys.
All right.
okay, I think
Well,
we're done.
questions? Last call. Any questions for anyone?
How will this apply for the close approach in of the asteroid?
Say that again.
How will this apply for the close approach of the Apophis whenever you guys try to track that?
Uh, Bill, correct me. I don't think we have any plans to track that, do we? Or any of the
Well, Adrian, I'm sorry, I don't quite understand what you're referring to. Which asteroid?
The Apophis close bypass that will be. I
Oh,
thought you were going to attempt to bounce a signal off of it also. This is the
uh,
Apophis in 29, is it? I don't know. Yeah.
I don't know. That's news to me.
well, I'll
Oh,
just make a comment
is Rick
on.
still on? Because I think he was the one that was had actually also proposed that.
And we're gonna probably do something with that. It's on the list.
I think you need to consider that, if that's in Horizons, then you can probably use System 1 to do it. But if it's not in Horizons, it takes software changes to try to track that thing.
That'd be an additional propagator that we don't have internally. That's why you would use Horizons.
So I think Horizons has some asteroids in it, but I'm not positive.
Yeah, I
Well,
guess that's
the reason I'm saying is because it'll be a close path to the Earth, so it's going to be moving at a pretty good clip. That's what the by essentially the essence of my question.
Right. Right now, our algorithms probably we've limited even the slew rate's limited to 4/10 of a degree a second, and tracking is more like limited to around 1/10 of a degree. So if it exceeds those, we're probably not going to be able to track it.
I just got on the Horizons database, and you can search on small bodies such as asteroids and comets. So we could use it as a pointing mechanism.
So it would be useful you can get it to generate ephemeris in the future. So it'd be if it could generate them near the time of when you want to track it, then you could see what kind of rates are it's incurring and see if that's within the realm of possibility.
And as an aside, we've been I don't think we've gotten a definitive decision yet, but we're thinking of throwing our hat in the ring for Artemis 3, though we won't be using the dish. Since it's a low Earth orbit, we really don't need the gain of the dish. And so we'll probably just go with, just like a Yaesu ASL mount with a Yagi on it. Also, the passes are going to be very short because it's going to be a low Earth orbit.
Well, that kind of relates to what I was trying to say because the Apophis pass will be underneath the geosynchronous orbit, so it's going to be going by pretty quick. So that's kind of what I was thinking. Just I'm not sure what the rate would be for being able to track that, but I was just curious if you had looked at it. That's all.
Would you be interested in crunching those numbers and find its maximum degrees per minute or second or whatever as it goes by? If you can give us those numbers, Lewis and Glenn would know if we can track it.
I'm not sure I could get a crack at that, but I can
Okay,
start looking
all right.
into
I'm
it.
just asking. I mean, that's ultimately what we need to know is
Right.
its angular velocity past the Earth.
Sure, and so I just thought since I thought this had been maybe a future plan that maybe that had been looked at, so that's what I was referring to.
Yeah, the
Well, the
Apophis,
fact that Rick said that he's looking at it is news to me. So that's good.
so Apophis is in the Horizons database, so you could run it through a date sequence and come up with the rates. The rate data would show up in the output if you program it correctly. So it does exist out there that it could be looked at.
Yeah,
Yeah, well, it's gonna be a major event, so there's gonna be several spacecraft going to it and so forth, and so it's just kind of like a major sort of astronomical event, and so there's a lot of interest in it, and so I assume that that might have been a potential target for attempting to do something in terms of not an Eve, but I guess you call it an Apophis Earth and balance, and so that's kind of the question that I was trying to refer to.
Have we ever done in the past, for lack of a better term, a radar bounce off of an object with Rick's timing hardware down there? I think that we now have that capability, but I don't believe we've ever done anything like that in the past.
we were working on doing a radar timing and distance measurement off the moon, which would be a pretty standard experiment.
Yep,
Mhm.
we got plenty of moon bounce.
It's gonna be 42 degrees per hour, the angular speed for that asteroid.
How much?
So degree a minute, we should be able to do that. Less than a degree a minute.
Yeah, a little bit less than degree, 42 degrees per hour. So yeah.
Huh.
Is that when it's passing close or the way it is now?
I think you're talking closest approach, aren't you, Vladimir?
Yes, yes, it's in closest approach, and it's gonna be about 20,000 miles away.
Oh, okay, yeah.
And what date is that?
Hold on, let me check.
It's going to be, I believe, on a Friday the 13th. It might be April 29, if I'm not mistaken.
Yeah, April 13, 2029.
Yeah, I think that's the date, right?
Friday the 13th.
Well, it was thought at one time that it was actually on a collision course with the Earth, which would have been really bad news for a lot of people. So, but it's just like I said, it's such a close approach, and it's a pretty good size asteroid. I think it's like maybe a couple of hundred.
There'll be a lot of hams trying it. for
Yeah, well, a
sure.
lot of I know the SEN is going to bounce signals off it. They're going to do radar tracking, radar visualization. They're going to do mapping, probably probably in conjunction with Green Bank and the DSN antennas. And there's going to be a lot of signals going on off of it. So, like I said, it's a big event. I just assumed that maybe that had been something that had been looked at for potential future project to do something.
Well, I
It
think,
sounds like it's going to be white hot in
yeah,
terms of RF.
yeah. Yeah,
Just
and
got to pick the right frequency. I don't think
yeah.
they'll be transmitting on the ham band, so
Well,
Yep.
Adrian, I think Roger was invoking the digital equipment mantra on you, which is the guy that makes the proposal does the work,
He who proposes disposes.
right?
Yep.
There you go. So give us a plan and what it'll take.
It sounds like talk to Rick, because it sounds like Rick's already thinking about it. Okay, anything else? As I said before, last call. Here we go. All right. Well, I want to thank everyone for showing up for the engineering meeting. We do have the science meeting 2 weekends from now, and Paul has sent out some emails about the content of that meeting. We've got the Thursday disassembly at Tiffany Square here in Colorado Springs at 10 o'clock on Thursday morning, 10 a.m. And I think that's pretty much it for upcoming stuff. I'm going down on Friday. Sounds like Bill might be riding down with me as well as Matthew. And if anyone else has stuff to do down there, you're welcome to come down that day and do your thing. We have a tendency to all go off in our corners and do the right or do our stuff when we're down there. So I guess that's it. Well, again, thank you everyone for showing up, and we'll see you either down there or we'll see you all at the science meeting in 2 weeks.
Good
Thank you
night.
for coming tonight.
Very good. Thank you, Roger, for setting it all up.
Sure.
Good night.
Good night.
Uh, hey, quick question. Can you guys hear me or no?
Yeah, we can hear you.
When is the disassembly at? Did he send out something for that?